Okay, so we are going to look at Gay-Lussac's law next. So Gay-Lussac looked at the temperature and pressure relationship, so he held volume and amount constant. So pressure and temperature. So pressure, we know, has to do with the collisions of gas particles, and temperature, we know, has to do with the speed of the particles. So let's think about what would happen if you were to increase the temperature. What would happen to the collisions? What do you think? If particles are moving faster, would they collide more or less? Would it be a direct or an inverse relationship? So to demonstrate that, I have a soda can here that is has a little bit of water in it, and I'm heating it, the goal is to vaporize that liquid water, so the can is filled with gaseous H2O. I'm going to go ahead and grab my goggles real quick. And a pair of tongs, and we want to heat it until we can see steam coming out. So at this point, because this is open, the pressure inside of the can and the pressure outside in the room are equal to each other. Because if I build up pressure inside of the can, then some gas particles can leave to equalize the pressure. Or if there's extra pressure outside of the can, some particles can go into the can to equalize the pressure. So as long as it's open, the pressure outside and inside should equal the same. Does not matter what the temperature is or anything like that. So what I'm going to do is, once it's done heating, when I can see the steam coming out here, I'm going to flip it in upside down into a bucket of ice water here. So, just my camera so that you can see my beaker of ice water. And I think it's ready, so I'm going to go ahead and take this and flip it. And what happens is the can gets crushed. Now, why is that? So, as we mentioned, before I flipped it, because this is open, the pressure in the room and the pressure inside of the can, gas particles inside of the can, are pushing with the same amount. That's why nothing was happening to the can. So the particles inside are pushing out on the can, the particles in the air are pushing in on the can, but they're pushing with equal amount, same pressure. What happened is I flipped it upside down, so now that I closed it, and I cooled it down very, very quickly, what happened is the water vapor inside now it became very, very cold. And so because it slowed down, the pressure went down. There were not as much collisions inside, and so the particles inside of the can were pushing out very weakly. The particles in the air were pushing in very strongly, and so because the outside pressure was higher than the inside pressure, it crushed the can. Atmospheric pressure is very, very strong. Again, almost 15 pounds for every square inch, so it's very, very strong. So this is a direct relationship between temperature and pressure. When I decreased my temperature, my pressure went down. It's a direct relationship. So when I cooled it, my pressure inside of the can got lower, and the pressure outside remained the same. So the pressure outside crushed the can in. Okay, so direct relationship between pressure and temperature. So let's look at Gay-Lussac's law in terms of words. So it says, as the temperature of an enclosed gas increases, the pressure increases if the volume is constant. So I have volume and amount constant. As I increase my pressure, my temperature goes up, or vice versa. The temperature goes up, my pressure goes up. Direct relationship. In terms of a mathematical equation, pressure is proportional to temperature. And so I can remove a proportionality symbol and put an equal sign and a constant. So P is equal to a constant times T. I can rearrange this to solve for the constant, so P over T is equal to K. So if I look at my first set of conditions, my pressure and my temperature, divide them initially, so P1 over T1, that's equal to a constant. If I change my temperature and pressure and divide them again, P2 over T2 that is also equal to a constant. So I can set P1 over T1 equal to P2 over T2. You can rewrite this in a different way. There's no reason why the pressure should be on top and the temperature should be on the bottom. So you can write it as T1 over P1 equals T2 over P2 with the pressures on top, the temperatures on top and the pressures on the bottom. You can also rewrite it as T1 over P1. T1, let me rewrite this. T1 over T2 is equal to P1 over P2. This is also a direct relationship. You can rearrange this equation to get this one. So any of those three versions work as long as ones are on the same side and twos are on the same side, whether left and right or top and bottom. As long as the ones are on the same side and the twos are on the same side, then that's a direct relationship. If we were to graph this, P versus T, it would look like a straight line like that if this was the Kelvin temperature. If that was the Celsius temperature, so let me redo that. There's Celsius. This is pressure, then it would be here. This would be negative 273 Celsius. That's absolute zero. So that's one of the ways they extrapolated to figure out what absolute zero would be, is they plotted some pressure and temperature points, and they extrapolated and saw where the pressure would be equal to zero, and that's absolute zero, which is negative 273 Celsius. Let's try a problem. It says a gas has a pressure of 1.47 atm at 303 Kelvin. What is the new temperature of the pressure changed to 680 millimeters of mercury? So 1.47, this is a pressure. 303 Kelvin, that's a temperature. What is the new temperature? So these were the first set of conditions. T2 is what we're solving for, and this is P2. So we're going to say P1 over T1 equals P2 over T2. The only problem here is that my pressures are at different units. So I have to change both of them to say millimeters of mercury, or both of them to say ATMs, or both of them into something else like kPa. Do whatever, as long as they both match. So I'm going to go ahead and change my pressure here to ATM. So 680 millimeters of mercury. Put millimeters of mercury on the bottom. ATM on top. 1 ATM is 760 millimeters of mercury, so this is 0.895 ATM. And so plug that in. So P1 1.47 ATM over 303 Kelvin equals, my P2 is 0.895 ATM over T2. That's what I'm solving for. So let's think about this. My pressure went down by about, a third or so. So what should happen to my temperature? It should also go down by about a third. A little bit over a third, I guess. So T2 ends up being 180 Kelvin.